So our next talk is by Vincent Contizer, and he's going to talk about security games.
Okay. Thanks, everyone. So this is work with a lot of co-authors, but I've singled out the two PhD students working with me here. Is there a laser pointer? Good. So that's Dima over here and Josh over here. So my talk is motivated by these recent successful applications of algorithmic game theory in real-world security domains. We're not the primary group behind that. The primary group behind that is Milind Tambe's team core group at the University of Southern California. So here's a picture of them. And so this involves things like airport security. So if you go to Los Angeles International Airport these days, for instance, the way that they decide where checkpoints go, where canine units go, is by running an algorithm for solving a particular game. And besides Los Angeles International Airport, recently they expanded their software so that it can deal with all sorts of other security scenarios as well. They're evaluating this at another undisclosed U.S. airport, and they're looking to deploy it at all U.S. airports. It's about 400 airports. They are also working with federal air marshals. So which flights actually get a federal air marshal. And now they just recently started working with the Coast Guard, and they're talking to a whole bunch of other institutions. So definitely seems like there's another decade of research left there. And it's kind of natural. It's a natural kind of application, I think, for game theory and algorithmic game theory in particular, because it's clearly a situation where you have parties with different interests. It's not necessarily zero-sum, but certainly not a cooperative game. And you really want randomization. You don't want your security placements to be predictable, so that's why they use randomization. So it seems like a good place to do some practical work. But what I want to talk about here is, well, what are really, from an algorithmic game theory viewpoint, what are the key technical aspects that make this interesting? And in my view, there's kind of two main parts. So the first one is the commitment aspect. So in all of this work, instead of just solving for a Nash equilibrium or something of the game, they actually take more of a Stackelberg model where the defender can commit to a strategy first, and then the attacker responds to that. So the motivation is kind of, well, you know, the defender, the airport security or something is running this every day, day in, day out for a long time. The attacker can observe for a long time and then eventually attack in a best response fashion. And so this commitment aspect takes a big role. So that's the first part I'll talk about. And the second part is these games have a particular kind of structure. They're not completely general games, and that structure can be exploited. It also poses some challenges. So I'll talk about that in the second part. So let me first talk about this commitment aspect. So here's a standard example of that. So probably many people have seen this before. So here's a very simple 2x2 normal form game. Very easy to solve. So if you look at it, you see that up dominates down strictly. And so the column player can anticipate that the row player will play up, and hence the column player will play left to get this 1. And so this is the unique Nash equilibrium. Actually, it's the iterated strict dominant solution of the game. So it seems there's not much to say about this game. But now if you kind of change the structure of the game, and you allow player 1 to commit to playing one of the rows before player 2 makes any move, then player 2 observes that and chooses a column based on that, it changes the game. And actually, the optimal thing to do becomes to play down, right? Because if you're the row player and you play down, what's going to happen? And the column player believes that you've committed to playing down, then the column player will choose to take this 1 instead of the 0 by playing right. And this actually results in a utility of 2 for the row player, right? So by committing to a strategy that would be dominated in the single-shot version of the game, you can do better. Okay, now any good game theorist should probably tell you that you should probably model this as an extensive form game as follows. Player 1 first commits to up or down, and then player 2 responds, right? And you can solve this by backward induction. You see that player 2 here would move left, here would move right, and hence the best thing for player 1 is to commit to down, right? So it seems there's kind of nothing that interesting going on here. Things get maybe a little bit more interesting when you think about commitment to mixed strategies. And this is really the model in which these security applications operate, that every day you draw from the same mixed strategy, but the realization that each day might be different. If you can commit to a mixed strategy, you can do a little bit better because you can do something like this. You can commit to going down 51% of the time and up 49% of the time. What's the point of that? Well, if you do that, the column player is actually still better off playing right and getting this one 51% of the time rather than getting this one 49% of the time. But it's better now for the row player because now there's also 49% of the time that she gets a utility of 3. Right? So now the expected utility is closer to 2.5. Right? Of course, it would be even more optimal to do 0.501 or 0.50001. And of course, in the limit, you're going to get 0.5, 0.5. This is kind of a tricky case because now you've actually left the column player indifferent between playing left and right. So you may not want to do that in a critical security application. But so from a theoretical point of view, this is kind of the optimal strategy. So what we're going to do is we're going to assume to actually have an optimal strategy well defined that the follower, the second player, the column player, breaks ties in the leader's favor. Right? So here the column player is tied and will actually choose right. And if you're not comfortable, well, the reason is that the row player could back off a little bit and play 0.51 instead and get it that way. And to be more precise, so if you have a generic game, you can basically do that. So in a generic game, that will actually be the unique subgame perfect Nash equilibrium outcome. And so we'll refer to this also as a Stackelberg mixed strategy because it's a Stackelberg model where one player moves first. Okay. And again, this argument that you should just model it as an extensive form game is still reasonable. It's just that now the extensive form game has become a lot bigger. So these were here before. But now player 1 also has the ability to commit to mixed strategies or to mixtures over actions, such as 0.5, 0.5. Right? And so this whole game has become bigger. And so you'll see that, again, in the backward induction solution, you get this outcome over here. There's the 2.5 again. And so this is a perfectly correct representation of the game. But from a computational viewpoint, it's not that practical because it's an infinite size extensive form game. Right? There's infinitely many distributions to which player 1 could commit. And so in that sense, we still use the normal form representation. So it turns out actually, that's the problem we're going to try to solve. So you're given a normal form game and you want to solve for the optimal mixed strategy to commit to. And it turns out that's actually not that hard. You can do that in polynomial time using linear programming, unlike, for instance, solving for a Nash equilibrium. And the algorithm is very simple. It works as follows. So without loss of optimality, we can assume that the second player will play a pure action. Right? And with that in mind, we're going to solve separately for every column, for every follower action. What we're going to solve for is, under the constraint that we want to incentivize the second player to play that particular column, what's the best we can do? Okay? And here's what the linear program will look like. So this is for a particular follower action T star. Right? So for a particular column, what are we going to do? We have these PS are the probabilities that we put on the rows. They have to sum to 1. Let me put this up here. The constraint is that for any alternative column that the column player might play, the expected utility that the column player would get for that is at most the expected utility that he would get for playing T star, which is the one that this particular linear program is for. And under that constraint, we want to maximize the expected utility of the leader. Right? So sub L means for the leader, sub F means for the follower. It's very simple, right? And so you have to solve this linear program separately for every column. It may be infeasible for some columns, right? Because we can, for instance, never get the follower to play a dominated strategy. But it will be feasible for at least one. And so what you're going to do is you have all these linear program solutions. You pick the one with the highest objective value. And that's going to correspond to your optimal solution. Okay. So here's the same idea visually. So here we have a game. Here's the probability simplex for player 1. Right? So these are the distributions to which she could commit. So player 1 picks a point in the simplex, basically. And there's different regions. So this region corresponds to... So in this region, the best response for player 2 is to play left. Right? In this region, the best response is to play center, and so on. And so this basically corresponds to the feasible region of one of the linear programs. Each one of these corresponds to one linear program's feasible region. And then I've drawn these arrows in here to represent the objectives of the linear program. Right? So this is player 1's utility within this region. This way is going up. Right? And so this will be the optimal solution for this linear program. This will be the optimal solution for this linear program. And this one for this. Right? And so what we do in the end is we take all these points. We look which one gives us the highest objective value. Here it turns out to be this, and that's the optimal solution. Right? So here the optimal solution turns out to be go half the time go up, half the time go middle. And what you're going to get is 2. so a very simple algorithm. So why is this a sensible kind of, so it's, in a sense, it's a different solution concept, right? You're given a normal form game, and you're solving it in a different way than if you're just solving for a Nash equilibrium. And what are some of the properties of that kind of solution concept? First, a good sanity check is if you apply it to a zero-sum game, a two-player zero-sum game, you're just going to get the same thing as you would have with Nash or Minimax, right? All those things are the same. If you think about it, the way you typically think about Minimax strategies, it's exactly commitment, right? You pick a mixed strategy, and the other player best responds to it. Another nice property is that this kind of mixed strategy commitment never hurts the leader, right? So committing to a pure strategy is often not a good idea, right? You don't want to commit to rock, paper, scissors. That's not smart. But you could commit to 1/3, 1/3, 1/3, and you'd be fine. And actually, that generalizes. So even in non-zero-sum games, it never hurts you to commit to a mixed strategy. And the argument is very simple, because you can simply, if you have a Nash equilibrium you like, just commit to that, commit to your strategy in that equilibrium. And by assumption, the follower is going to break ties in your favor, so you'll be at least as well off as in that equilibrium. And then, so there's this tie-breaking assumption. You can kind of prove it without that, and von Stengel and Zamir do that. And actually, they also show that it's no worse than any correlated equilibrium. Okay. And more recently, I guess we found kind of a deeper reason behind this. So if you look at the linear programs that I just showed you, you can kind of merge them all into one single big linear program. And what you end up getting actually is the correlated equilibrium linear program formulation, except with the incentive constraints for player 1 dropped, and with an objective of maximizing player 1's utility. Right? So that's another way to think about this, which is nice, I think, because it opens the possibility that techniques developed for computing optimal correlated equilibria might be useful in this kind of context as well. One thing that I think is very helpful is that in this model, there's no equilibrium selection problem, right? So in general, in games, you might have multiple equilibria. Now, which one do you play? But by changing the model to this kind of leadership model, that issue goes away because basically the leader dictates where we're going to end up. From the perspective of approximation algorithms, I think it's also nice. We have, because the best response problem for the follower is easy, it's very easy to evaluate how good any particular mixed strategy to which you might commit is. And so that's nice, and I think that's a little bit of an advantage over things like epsilon Nash equilibrium, where it's always still a little bit uncomfortable to assume that both players will be okay giving up some of their utility, and what if they don't, and what if they suspect that the other one isn't, and so on. That all kind of goes away here. Of course, the downside of it is, well, we really need to be sure that we can actually commit. And so I'll say a little bit more about that, right? That we have this commitment advantage, not only that we can commit, but also that the follower will observe this commitment and respond to it. Okay. So I want to briefly talk about some other work that we've done in this context. So we've also looked at commitment in extensive form games, computing optimal solutions, optimal strategies to commit to in extensive form games. You might have seen this at EC last year. Also Bayesian games. So Bayesian games here in particular, we look at settings where we're not sure about the follower's utilities. Typically you wouldn't be. Excuse me. So instead you have a distribution. And actually, that's the model. We already had this in the first paper. Excuse me. In the first paper on computing optimal strategies to commit to. But that's the model that they actually ended up using in the LAX application. They had a Bayesian game there. Once you talk about not being sure about the follower's utility function, another natural thing to look at is learning the follower's utility function. Right? So you might say, well, by repeated interaction, we can figure out what this utility function is approximately, and then learn to play better. And finally, we have a model where, so if you're not quite sure if the commitment is actually observed, that changes the structure of the game. And you can model this in a larger extensive form game. And so recently, we've been working on how do you solve that kind of larger game. But I want to move on, and I want to talk a little bit about this other direction. So what are the structural properties of these security games that are interesting and that we can exploit from a computational perspective and also from a game theoretic perspective? And so, I mean, on the one hand, that structure could be an advantage, but on the other hand, it can also be a disadvantage in the sense that the natural representation of one of these domains may correspond to a normal form that has exponential size in that natural representation, right? And in some applications, actually, it's okay that you can. So even in the original LAX application, they just had a Bayesian game in the standard representation of a Bayesian game, and that was still small enough that they could solve that directly. But in some of the later applications, that really wasn't feasible anymore. Once you look at the federal air marshal's problem, there's so many flights to defend and so many federal air marshals to assign that just writing down the normal form of the game, even if you don't worry, even if you just estimate point value for the follower's utility function, it's just not doable to write down this representation anymore. And another one is protecting a city, which maybe I'll have a little bit of time to talk about. But so the problem is that you have some resources to assign to some targets, and every one of those allocations is a pure strategy in this domain, right? And so you have exponentially many pure strategies, so you're kind of dead in the water if you're going to try to use a standard representation of a game. So then what is a more natural representation of these kinds of games? So one that was proposed by the USC group is this. This is a security resource allocation game, and it works as follows. So there's some set of targets, T. There's a set of security resources, which we call capital omega, which are available to the defender. And again, so in all this work, the defender is the leader, right? Has the Stackelberg advantage. There are subsets of these targets that we will refer to as schedules, right? So a schedule is a set of targets that can be simultaneously defended by a single resource. So in the context of federal air marshals, for instance, you assign a federal air marshal to a tour, which includes several flights, and so all those flights will be part of the same schedule and defended simultaneously in some sense by the federal air marshal. Okay, then in general, resources will have limitations as well. Not every resource can defend every schedule, so that's indicated here. So this resource can defend this schedule or this schedule, but not both. Okay, and then finally, so that's the defender strategy space. The attacker is just, in the basic model, is just going to choose one target to attack. And that's going to determine the utilities. And now there's this particular form that the utilities take. The utility for each player depends both on which target has been attacked and also whether that target was covered or not covered. Right. So covered means that it was defended, and uncovered means that it was not defended. Okay? And then we assume holding the target that was attacked fixed, the attacker prefers it to not be covered, and the defender prefers it to be covered. Right? That should be natural. But notice it's not zero-sum. No, not necessarily zero-sum. And actually, in these applications, they really need the non-zero-sumness of it. Okay, so how do we solve these kinds of games? And so the first thing to notice is that the number of pure strategies for the defender is exponential, right? Because there's exponentially many allocations. Here there's still a polynomial number for the attacker, though if I get to it later on, we'll talk about more complex attacks as well, where that becomes exponential as well. So the first thing that has been tried, as is actually what the USC group tried, is let's have a different linear program formulation where the variables, instead of being the probabilities on pure strategies, the variables are going to be the marginal probabilities. So the probability with which a particular resource omega is assigned to a particular schedule S. And then can we do a similar kind of thing? So here's basically what they did. It's not quite the same. They had a mixed integer program formulation, but I'm presenting it here as a collection of LPs just to tie it up better with what I presented before. So here's an attempt at it, and let's see if it works. So again, we're going to have these distributional constraints. Every resource omega can be assigned at most once. Every target can be defended at most up to 1. And then given that, we want to maximize the leader's utility, the defender's utility, with some and again, so there's a separate LP for every possible attacker strategy, which in this case is a particular target T star that's attacked. Okay? And so given that T star is attacked, there's going to be some probability with which it's covered, and in that case, the defender will get the covered utility, and some probability with which it's not covered, and then that's going to be the utility, right? And then this is supposed to represent the probability with which a particular target T is defended. So you sum over all resources, and you sum over all the schedules that have that target in it, and that probability, right? But this should strike you as being a little bit wrong, right? Because this is assuming that those are disjoint events, right? That if one resource covers it, another resource is not also covering it at the same time. Because if it is, then we're double counting. So we'll look at that in a second. But if you assume that that's right, then also here you would have the same attacker optimality constraint that the attacker is not better off attacking some other target C. Okay, so it actually turns out that this issue of double counting probability is fundamental. You can't always get around it. So here's an example where you can't get around it. So in this particular example, we have 4 targets. We have 2 security resources, omega 1, omega 2. Omega 1 can cover horizontal schedules, right? So for instance, omega 1 could cover both of these targets simultaneously or both of these targets simultaneously, but not both. And similarly for target omega 2, for resource omega 2, it can cover the vertical schedules. So either these 2 or those 2, but not all of them at the same time. And so if you take that linear program that I showed you before, what it's going to tell you is, well, you should do 50-50 for both of these. And I mean, more crucially, what it's going to think is that actually covers every target completely, right? Because it says, well, the total probability that this target is defended is 0.5 plus 0.5 is 1, right? But so it thinks that every target is completely defended, but common sense should show you that, well, here you can obviously defend at most 3 of the targets at any time, right? And so that indicates that it's not going to work generally. But in some cases, actually, this program does turn out to work. In particular, for instance, if every schedule has size 1, right? So this means that you're assigning resources not to combinations of targets, but you're just assigning them to individual targets, which in some applications makes sense. Then you can actually do this. So what you use is the Birkhoff-von Neumann theorem, which probably many people know, but let's go over it. So the Birkhoff-von Neumann theorem says take a doubly stochastic matrix, so all the columns sum to 1, all the rows sum to 1. Then there's a decomposition of this matrix as a convex combination of permutation matrices. And a permutation matrix is just one that has 1, 1 in every row and 1, 1 in every column. Right? And this will turn out to be useful for us. And this decomposition is small, and it can be found in polynomial time. And actually, we'll need a slight generalization, which is very easy to obtain from the main thing, which is that if you take a doubly substochastic matrix, meaning that every column sums to at most 1, every row sums to at most 1, then you can also decompose it in a way such that in a 0-1 matrix where every row has at most 1, 1, and at most every column has at most 1, 1 as well. And that's actually what we'll need. Why does this work? Well, if you take that linear program from before, so here's a particular instance that we might face. The linear program is going to return you something like this, while you should assign resource omega 1 to target T1 with probability 0.7 and so on, right? But it just gives you these marginal probabilities, and you have to make sure that those things, that the event that one particular resource defends a particular target, and that another resource defends that same target, that those events are disjoint. But Birkhoff-von Neumann will actually give you exactly that, because you just decompose this matrix as follows, right? So and these matrices, because they have at most 1, 1 in every row and column, will actually correspond to valid allocations, valid pure strategies, and they each get their weight. And this way you also get the right marginal probabilities that you need. Good. So size 1 you can actually do. More generally, here's the complexity of the various cases. So we looked at different sizes of schedules, right? So I just told you about the size 1 case. We also distinguished between homogeneous resources and heterogeneous resources. So homogeneous resources is the case where every resource has the same set of schedules to which it can be assigned. Okay. So this is what I just told you. Of course, the homogeneous case is no harder. In the heterogeneous case, basically, the moment you move beyond that, it's going to become NP hard to solve optimally. Then it turns out that in this case, where the schedules all have size 2, and actually the schedules are the edges of a bipartite graph, that you can also do in polynomial time by a different application of the Birkhoff-von Neumann theorem. Actually, more generally, there's a separation oracle for the case where schedules have size 2 without any further restrictions. But with size 3, it's very easy to see that it becomes hard by reduction from 3 cover. I want to talk a little bit about So I've talked about computational aspects of these games, but because these are a particular class of games with their own structures, it also makes sense to look at them from a game theoretic angle and see, well, what kind of properties do they have? What can we say about it? And in particular, a nice thing to look at is, is playing Stackelberg really the right thing, right? Because it's making this argument that, look, the defender every day in and day out, draws from the same distribution, and the attacker could learn this over time by observing, and then best respond. So that's the argument, right? But in some of these applications, that argument is a little difficult to make. For instance, with federal air marshals, they actually try to keep the federal air marshals undercover. So how are you supposed to observe, right? And so those are debates that people are having. So can we say something about this? And actually, it turns out that this whole issue doesn't really matter much in security games of the kind that I just presented to you under minor condition. In particular, we have this result, which says, so there's one condition that we need, which is that any subset of a schedule is also a schedule. That means that if I'm able to assign a resource to this one particular set of targets, if I drop one of those targets from that set, that's still going to be a valid schedule for that resource, right? So I can choose to kind of not defend something in a schedule. And if that's true, then you will have the property that every Stackelberg strategy will also be a defender-Nash equilibrium strategy, right? So even if you did want to solve a simultaneous move game where you wanted to solve for a Nash equilibrium of this game, the same algorithm will work. You will get the same. That strategy will still be a Nash strategy as well. And so now you might worry, well, now you have, if you're talking about simultaneous move games, now you have an equilibrium selection issue again, right? How do we know that we're playing the right equilibrium, that the attacker isn't playing from some different equilibrium? That turns out not to matter either, because these games have the interchange property that if you take two Nash equilibria, I'm playing according to one Nash equilibrium, you're playing according to a different one, the result will still be a Nash equilibrium, just like you have in zero-sum games. So in some sense, these games are kind of like zero-sum games. And actually, the proof works by transforming it to a related zero-sum game and then transforming it back. One more thing to talk about is multiple attacker resources. So I briefly hinted at this before. So all the models I talked about so far, there we have a single attacker resource. So the attacker is going to choose a single target to attack. Generalizing that a little bit, we might have an attacker that has k resources and so can attack k targets at the same time. So in our model, which you can debate, but so our basic model says that the utility that the players achieve from k targets being attacked is just the sum of the utilities that they would have achieved for the individual targets. And so in this model, actually, the properties that I showed you before break down. So Stackelberg strategies are not generally Nash strategies anymore. I have an example. I'll skip over it for time. It's interesting that actually now the situation is reversed in the sense that in this model, you can compute a Nash equilibrium in polynomial time, but you can't compute a Stackelberg strategy in polynomial time unless p equals np. Which is interesting because in the normal form setting, it's reversed, right? Because there we can solve for a Stackelberg strategy efficiently, but solving for a Nash equilibrium is p-pad complete. I'll skip over this. OK, so I just want to conclude. So I'd argue that these security games, they're a really nice and very visible application for algorithmic game theory. They generate a lot of interesting computational problems, but hopefully I've also convinced you that there's interesting, fundamentally game theoretic questions, right, about the game theoretic structure of these games to be addressed. And they actually have, and it's interesting because with this being deployed in the real world, you really run into those questions. Can you really commit in this kind of situation? And you have to deal with them, right? Normally, we're all aware of equilibrium selection being an issue, but we're not really forced to deal with it. And here you have to deal with it one way or another. One thing I haven't really talked about is that, of course, these real applications introduce a lot of practical issues. For instance, how do you get the attacker utility function? You probably also want to worry about robustness, right? So if you just straightforwardly apply one of these algorithms, you're generally going to get a very not robust solution because it's going to push the attacker to be just about indifferent between two actions. And if they take the wrong one, you're much worse off. You might worry about behavioral issues, right? So you may have a human attacker who doesn't necessarily play optimally. There's tools corresponding to these things that people have to use that nobody, right, that people have to use that have never taken any game theory, so they have to deal with that as well. All right, so let me finish there. Thank you.
Since we are behind schedule, only one short question.
Could you elaborate briefly about the actual game, real-world game being played here?
Right, so they have this kind of structure. So I don't know the utilities. Even the USC group doesn't know the exact utilities because they're not privy to them, right? So there's another group that's actually coming up with the utilities and that feed into that algorithm. So I'm not sure exactly whether I'm answering your question or.
Who are the sites? What are they playing?
Oh, sorry. So for instance, in the LAX example, there's a road network into LAX, and there's different places where you could have checkpoints, right? So which roads get a checkpoint? There are so many checkpoints to allocate, and if you don't allocate a checkpoint to a particular road, then in principle an attacker could come through there and not be observed. An attacker could be a terrorist, but it could also be a drug smuggler or something else. Right. And yeah, of course the hard thing is to come up with those utilities, but they have other people doing that.